So before I start actually today's session, I would like to add one thing related to the problem which we were discussing last time. So if you remember in last session, we were solving this problem in which there was a particle which was moving with a velocity 50 feet per second for first 4 seconds, and then from 4 seconds onward its acceleration became minus 10. Constant velocity means that it has zero acceleration, right? So for first 4 seconds acceleration was equal to 0. For 4 seconds onwards the acceleration became minus 10, right? And it is a constant acceleration case. So we actually divided our motion in two parts. First was when t was from 0 to 4 seconds. We had a equal to 0, but then from 4 seconds onwards here you see that we had a equal to minus 10. So acceleration is constant, but it has two different values for two different ranges of time, right? So what we did actually was that we followed the case A methodology, integrated that constant acceleration to get velocity, and integrated that velocity one more time to get displacement, right? If for example we look at the displacement equation which we derived is minus 5t square plus 90t minus 80, right? It is determined by successive integration of constant acceleration. But if you look at that equation, it tells us that maybe there is some initial displacement, because for example let me write s here, it was minus 5t square plus 90t minus 80, right? So if you put t equal to 0, you will still get a non-zero s, right? You will get s equal to minus 80 feet, which first of all contradicts with what was given in the problem statement. In problem statement it says that at the origin when t is equal to 0, so which means when t is 0 the object is at origin, which means it has no displacement, 0s, right? So first of all this equation seems to be contradicting with the initial statement. And second thing, that when we actually apply the closed form expression which we derived for case A, that was actually s is equal to s naught plus v naught t plus 1 over 2 a t square, right? When we apply this equation for a equal to minus 10 feet per second square, which is given in this problem, v naught is equal to 50 feet per second, the initial velocity. When we put those numbers, we don't get this equation which we derived following the same idea like successive integrations 2 times, right? This scenario will repeat again and again in many tutorial problems and also in many midterm or final exams also. For example, you will be given with the case like from point A to B you have acceleration of this much, and then from B to C maybe to another point you have another acceleration. So it may be a constant acceleration case, but the whole motion is not having a constant acceleration throughout. So therefore you have to divide your motion into two parts, like your whole problem should be divided into two parts. First part should be only for t equal to 0 to 4 seconds, which is a very simple case. Acceleration is 0, which means you will be simply having s is equal to vt, where v is a constant value for first 4 seconds. For second part, your time is not starting from 0. And if you look at this equation which I am encircling now, the relationship which we derived in case A was actually based on an assumption that time is starting from 0, right? So when we go back to our case A derivation, this one, this one. So if you look at that, we start with t equal to 0, our starting t is 0. So whenever we put a limit on t, we start it from 0 to t. So we get velocity versus time relationship for a case when t started from 0. Similarly, when we integrated velocity again to get distance, that equation, that also was based on when time was starting from 0, right? So they actually, both of these equations are only applicable for parts of the problem or for full problems where acceleration remains constant throughout the motion, right? If for one part of the motion acceleration has one value, other part acceleration has a different value, you must divide your problem into parts. But then also for first part you may be able to directly apply these equations, because for first part t will actually start from 0. But for second part, like in that particular problem from 4 second onwards, you may not be able to directly apply these two equations because they are not applicable, they are derived for the case when t started from 0, right? So that is actually the reason when you actually use the formula directly for the second part of your motion, this formula, when you directly apply to your second part, it won't give you the same s versus t relationship because it was derived for the case when t started from 0 and the second part actually started from 4 second onwards, right? So this actually made me to re-derive the same two formula for case A when t was not equal to 0, right? Someone may actually want to have a closed form expression for that case also, when t is not starting from 0 but have some finite value, right? So what I did here is that I re-derived the case A, right? This is same case A, constant acceleration, but this time I repeated the same process by assuming that the starting value of t is not 0 but some number t1, right? And we want to derive a v versus t relationship and s versus t relationship for the time after some time t1. So obviously t1 is less than some t, right? And now what I am doing, I am repeating that same process like integrating the constant acceleration, but not from 0 to t, but from t1 to t, right? Where t1 is some number less than t, right? I evaluated that integral, put in the limits from t1 to t this time, I get a slightly modified equation for velocity versus time relationship, right? And then I repeated the process, like integrated this equation again, this velocity as a function of time, I integrated it again from again t1 to t, and I get the displacement equation, which is this one which I am highlighting now, right? So in this equation t1 is your starting point and the value of displacement at time t1 is s1 and the value of velocity at time t1 is v1, right? So the summary is that if the t is starting from 0, you have these two equations, right, which we derived earlier. You can readily apply them to a case, but please make sure that time is starting from 0 and the acceleration remain constant throughout the motion on which you are applying this expression. But if you have to divide your problem into some parts and you still want to apply the direct equation or direct expression, then you can use these two equations which I kind of re-derived in this PDF file. You can see that, and they are modified from the original two equations. Wherever there is t there, you have t minus t1, where t1 is the starting value of time for that case, and the corresponding displacement and velocity values are s1 and v1, right? So if someone is really interested in directly applying the expression for constant acceleration case, you then will have two sets of equations. One will be governing the motion from 0 to a time t, but the second set will be governing the motion from some time t1 to any time t, right? Two sets of equations to the problem we were discussing last time, and we knew that for first 4 seconds a was 0, for 4 seconds onwards a is minus 10, right? So which means if we want to consider this problem as the constant acceleration problem, then we should divide our whole motion into two parts, 0 to 4 and 4 onwards, right? And let's say that now I want to solve the same problem by directly applying the equations we derived for constant acceleration case. Let's assume that we don't want to repeat that successive integration or apply the solution technique, but directly want to use the expression. So what I did here for clarity, I call part 1 of the motion as 0 to 4 second, part 2 of the motion from 4 second onwards. For part 1, I applied the same original equations which we derived earlier, right? So V is equal to V naught plus AT, S is equal to S naught plus V naught T plus 1 over 2 AT square, where S naught and V naught are the values of displacement and velocity at T equal to 0, exactly at T equal to 0. So when I put that information and use those equations, I get S equal to 50T. Acceleration was 0, so the second term simply cancelled out, so it became 0 here. When I apply the equations to second part, actually I should apply two modified equations, this one and this one, which I derived recently in this file. So now my T1 should be 4 second, my S1 should be the value of displacement at 4 second, and V1 should be the value of velocity at 4 second, right? So when I apply these two equations, directly put in the numbers, these three numbers, right? V1 was 50 feet per second because it remained constant for first 4 seconds. So at 4 second it was 50. And exactly at 4 second, the displacement would be 200 feet, constant velocity multiplied by the time 4 seconds. So it will be simply 50 times 4, right? 200 feet. So when I put in these numbers, I exactly get the same two equations, this one and this one at the bottom, which we derived by first principle also. By first principle, I mean by originally integrating the acceleration successively, right? So I realized that this is some additional technique which you should have in your skill set for problem solving. So therefore, I added it to this problem. If someone is interested in directly applying the expressions for constant acceleration case, then you have two different sets, right? You cannot simply use these two equations everywhere or in all scenarios. So for example, now for 0 to 4 second, I have a different S. For 4 second onwards, I have a different S. So if I plot them together on S versus T relationship, so this is my S versus T relationship like graphical form. So now I know that from 0 to 4 second, I have a different equation which is governing the motion, which is equal to 50t, S is equal to 50t, a linear equation. The second part is actually starting from 4 second onwards. So I have a different equation derived for that second part, right? And that is a second degree equation, right? So therefore, putting t equal to 0 in this equation and saying that S is equal to minus AT would not be correct, because this second equation is not developed for first 4 seconds. It is not governing the motion or describing the motion in first 4 seconds, right? So we cannot simply put t equal to 0 in this equation. This equation is actually starting from t equal to 4 onwards, right? Putting t equal to 0 would actually give you some hypothetical number, because this second degree polynomial would go back in minus, and maybe at t equal to 0 you will have minus 80, but that wouldn't be a right thing to do in this problem. So in short, your complete motion is described by a piecewise function. If you really want to summarize the S versus T relationship into one function, that would look something like this. S is equal to a piecewise function. It is equal to 50t for first 4 seconds. So t from 0 to 4, it is equal to 50 times t, a linear motion. But it is equal to minus 5t square plus 90t minus 80 for t greater than 4, right? So this piecewise function which means a function which has two different parts for two different ranges of independent variable, which is time in this case, right? So for one range of independent variable, you have a different function, and for a different range, you have a different function. So this is a piecewise function. So this will be the complete description of S versus T if someone really want to write it in one equation, right? One last thought experiment is that if you want to plot acceleration which is given here versus time, it would look like this on the same scale. A versus T, for example, you want to plot, it would look like this. It will start from 0, right, 0 value, and at 4 seconds exactly, it suddenly will become -10 and then remain constant for up to any time t, right? So it's -10 here, but it remains 0 for first 4 seconds, and then up to any time t, it remain constant, like maybe up to any indefinite time t, right? So if you look at this equation, this graph also, this also is like a piecewise function. I can describe it mathematically as a is equal to 0 for again 0 t equal to 0 to 4, and it is equal to -10 for t greater than 4, right? So now if you describe acceleration in this form, this problem will no more remain a constant acceleration case, because now you have a as a function of time. It depends on what value of time is, right? So for first 4 seconds it has a different value, and then suddenly it change its value. So if you don't divide this problem into two motions or two parts, consider it as one motion, then this will not become a problem of constant acceleration. It may become a problem of when acceleration is given to you as a function of time, right? And that will be a complex case. So therefore it is always a good idea to divide your motion into number of parts, and in each part you apply any equation or idea separately, right?